everyone. Good morning. Welcome to our session, Optimizing Processing from Edge to Cloud. Today we have the pleasure to explore this journey of data from Edge to Cloud, where scalability and accessibility really comes into the play. These talks that we will hear today touch on real challenges such as cost, speed, reliability, and they will demonstrate how this solution can directly benefit Earth observation, crisis response, and many other applications. I am Edoardo Ramalli from the European Commission General Research Center, and together with me, I'm co-chairing this session with Lev.
Good morning. My name is Lev Lapkis, and I'm head of Latvian Space Industry Association, and also I'm managing European Space Agency Business Incubator.
Thank you. So let's get started. We have our first speech from Alejandro from Thales Alenia Space. Alejandro, thanks you for joining us today, and the stage is yours.
Thank you so much. Well, I will start from the edge. From the beginning, where the data is produced. So I will introduce you a mission from Thales Alenia Space that is called Imagine-E. Imagine-E started last year when the launch was in March. It's a demonstrator for space edge computing that is deployed on the ISS externally in the Economist module. It will be operational till mid of October, so 2 more weeks. We have, apart from the edge computer, we have 2 sensors there, a hyperspectral camera and an RGB camera. So after the launch, when we power off on everything, we discovered that the hyperspectral camera was not working. It's not powering on. Probably during launch it was affected. So we tried to our second option, that was the RGB. This was our plan B. So when we power on and make the first capture with the camera, we discovered that these were the results. So, you know, it was an Earth observation experiment with one of the camera not working and the other one in this way. So we had no plan C at that moment, so we started thinking how to solve this. And the only way to correct it properly was to adjust the camera with a screw. Of course, externally in the ISS, it's not that easy to do it. So the other way was just to modify the images with software. The problem is that the mechanical defocus, the kernel was not known, so the intensity of the blur was not known, the nature of the blur was not known, and the other problem is that in the ISS, the experiment externals, the ones that are outside the ISS, are connected using a robotic arm, and the orientation is not known initially. So with this, it's really difficult to understand what you are seeing with these kind of images without knowing what you are looking at. And of course, this kind of images are not useful for anything at all in this way. So we started to think how to solve this, and the resources we had at that moment were these ones. So as you can see, not much for the powerful AI models we are used to using here on ground. So with this, we started from the beginning. We were having no data, no algorithms, nothing really. So we created a data set for start playing. We grabbed some images from Sentinel-2, both top of atmosphere and bottom of atmosphere. We downsample it in order to match our resolution and the attitude of the ISS. That is a bit different from the Sentinel mission. And we add some random noises in order to make them look similar. Again, similar. The kernel was not known at all. And we built this, this data set with clean images and blurry, imaginary-like images on the other hand. So for this, we created this kind of training framework. We use the MIMO-UNet model that is really optimized for real-time deblurring. It's not meant to be used on satellite images. It's for normal images in RGB. But we tried and we found that it was working. And for training, we embed this in a GAN. We use the MIMO-UNet as a generator of the GAN. And we add a discriminator and multi-scale also because MIMO-UNet is working in multi-scales, in different resolutions of the image in order to match the quality of the different resolutions of the outputs. And we add to the loss for training the generator, we add also some perceptual loss using a BiDS'25 that we train using Sentinel-2 images because, again, BiDS'25 is a general purpose model, is not for this kind of data. So we created a loss that was a bit more complex than the original one, and we trained the MIMO-UNet. So these are the details for the training. What is important thing here is that although these are the image dimensions and the patch image, the patch size of the images we were using on the model, one of the key things we have to determine was the size of the patch before downscaling the patches, because if you take small patches for this, the image is so blurry that it has no enough context information for solving the problem. So if you extend too much, the network starts to invent too much things, and you don't want that also. So that was the main variable to decide here. So the results were really good. Initially, we started with, as I said, with Sentinel-2 images using a structural similarity index, point signal to noise ratio. We saw an improvement, a huge improvement in the solution. Of course, that doesn't mean that it could help with the real images. So for the real images, as we have no current image to compare with, we use another metrics, in this case, Nick and Brisk, and they are giving the quality of the image without the reference. But we also, the improvement was consistent, both in the real images and in the synthetic ones. So these are the results, the good ones. On the left side are the original images, and on the right side, the improved ones. Of course, not all of them were with this quality. These were the ones that were failing. Initially, the model is producing some artifacts, mainly on some clouds, some specific clouds, not in all of them. As you can see in the first picture, some clouds are properly translated and improved, but others has this kind of roundings that are fake. And of course, the worst ones, the model is getting crazy when the scene is fully covered by clouds, or you have some blank patches like water or land without anything else. But with this kind of images, although the quality is still low, for other applications, if you extract the borders on the image, the borders start to appear. And if the borders start to appear, you can use other algorithms for downstream tasks to extract, to segment, to find objects, to do other things. That was the original idea of the mission. So you can see this here, for example. It's another app that is running in Imagine. It's running inside the edge computer that is using our images to segment the clouds. As you can see, although the worst images we were producing, and that looks really, really bad in comparison of what we were expecting. But in any case, the models are able to extract some information and to segment. This is also true for other apps that are finding body body water on the images, and also we are trying to some change detection that, of course, for big areas, for big things, it is able to find changes. For small objects, we are losing due to the resolution. We are losing the details. And of course, as it is a generative model, sorry, as it is a generative model, it is not outputting all the time exactly the same results, and there are some minimal variations around the object. So if the object has enough size, it is able to extract and to segment and to find objects. So, of course, as the quality was not the best one, but with this method, we realized that, on the one hand, it is possible to run this kind of complex models on board without any issues. It's running in a couple of minutes in real time. So the apps are requesting captures. The captures go through the pipeline. They are deblurred and returned in a clean way. So it is properly working as we expected for this. We have improved the quality pretty much, taking into consideration of where we started. And also, it is still useful. These images are still useful for some applications, not for everyone. We have to change some apps because they has other objectives, but for some of them it was working. And And finally, we will release, as I said, the mission is ending in 2 weeks. We will release the data, all the images, the regional ones, because I think it's an interesting problem to solve. And blind blurring, when you don't know you don't have a reference, it's a field that has still no solutions. And I think this could happen to any mission. It's good to have somewhere and a data set to explore and to experiment. That's all. Thank you.
Thank you, Alejandro. We have just the time for a question from the audience. In the meanwhile, I can ask you something like, how much effort do you need to put in this project to break the 5 minutes processing times that is actually required right now?
Well, in fact, we have two computers on board. One is the more powerful, kind of powerful Raspberry Pi. That is where the apps are running. We have enough resources there. And the other is a small computer that has the resources I show here. The idea was to have a model that was compatible with both platforms, just in case. Initially, we were not able to run on the powerful one, so the idea was to freely move from the processing from one part to the other. Nowadays, we are moving this model to the second computer, the powerful one. So we have reduced these 5 minutes to less than 1 minute for the processing. So again, without acceleration, it's pretty good.
Pretty interesting results.
Thank you.
So if there is no other question, I would like to thank you, Alejandro, for coming. And
Thank you.
Thank you. And our next presentation will be given to us by Richard Hofmeister from the company Verum Software and Systems from Germany. And the topic is Sentinel-1C data processing with a scalable science mission framework. Please, floor is yours.
Yes, thanks. Hi, I want to talk about Sentinel-1 data. We have seen lots of many applications, interesting talks on Sentinel-1 data, and I want to give an insight how this is produced. I take the opportunity of this year's BiDS because there was a new unit launched end of last year, the Sentinel-1C, and I want to give you insight how our team, which is responsible for the data production, deals with the daily work. My name is Richard Hofmeister. I'm part of this team at Verum Software and Systems. It's a medium-sized company in northern Germany, not very well known, I guess, but it's near Hamburg. We are 140 employees in total, but our Earth observation expert team is about 25 experts. So I will start off with a beautiful picture by ESA on all the Earth observation missions, with the science missions in greenish color, the Copernicus operational missions in blue color, and the meteorological missions in orange color. We are round about there where the white stripe is so far, and I further zoom in, and sorry for the HumanSat colleagues, leave out the meteorological part here. My title says we are using a science mission framework, and actually the software framework that we use here is originally developed for the EarthCare mission. It's a science mission for the Earth Explorer EarthCare with a quite complicated production model, actually. Implemented in 2017, the software, actually the working title is OLIP, Orchestration Library, not very fancy. But this was successful, and we adopted this framework for a few other missions, like the Biomass mission, launched this year. The Swarm mission, which is still flying, and it took up this modern software framework to continue its work. It will be used for the Flex mission to be launched next year, and that's the idea of my talk. Also is adopted for the Sentinel-1C production. We also made a general version of this software. It's also open source. Please approach me if you want to know how to download it, to be used for the next Earth Explorer missions, maybe Forum. Let's see. So the Copernicus ground segment is a collaborative ground segment, and the production service is one of the puzzle pieces out of this whole ground segment, and it's responsible for collecting the input data for the systematic 24/7 production, for an efficient orchestration, of course, metadata enrichment. We need an operator interface for our operators. We need a dissemination interface, and we need to integrate all the processing algorithms. And I made this figure with the puzzle pieces, and it started to draw lines, but there have been too many lines between all those puzzle pieces. Therefore, I removed those and just put in the relevant ones for our service. The data comes into the system through the acquisition services, and then the production service produces the products and disseminates the products to the long-term archive, to the Copernicus data space ecosystem that we heard of yesterday, and registers all those products in the traceability service that's kind of linked or part of the data space ecosystem. I think I talked about this already. So we did the software development, we implemented the service, we procured the infrastructure. In this case, the whole Sentinel-1C production runs on OVH Cloud computing infrastructure in Germany. And where we operate the service 24 hours with a DevOps team. So our developers and our operators are basically sitting in one room, so to say. The production model of Sentinel-1C is also not a very complicated one. So for those who know the EarthCare model, that would fill the whole slide with lots of puzzle pieces. In this case, I think it's probably mostly known to you, but the new one is the upper one. So after the level 0 production, there is a new product, the ship identification product that is calculated. Then we produce the ground range detected GRD products, the SLC products with the phase information inside. Then there's the enhanced time accuracy auxiliary data for the SLC data. And finally, the level 2 products with the derived quantities like winds over the ocean, for example. Of course, I also brought a schematic of our system. That's, I think, is very similar to all other production systems on the world that are existing. I want to mention 3 important points here. The middle one is the orchestrator. That's the heart of the system to hand the workflows to the relevant compute nodes. There is a monitoring facility that's very important for our operators to look at the running system and get all the information on one view, or say on a few screens, how the system works. And then the lower part is the storage management. I think this is also key to make the system efficient, that we handle the storage such that when multiple steps deal with the same data, we keep those locally near the computing to not to copy data over the network again and again. So I brought a few screenshots. One is from the monitoring dashboard, the acquisition monitoring. That's for operators to see which data came in, and then if the raw data from the acquisition has received successfully. There's another screenshot showing the compute nodes and how the system scales on the infrastructure. That's always interesting to see, and say every time when we get a new acquisition, the computer nodes start to produce the products. There was a new feature of the Sentinel-1C, and it will also be on the Sentinel-1D unit later on, which is the ship identification. So the Sentinel-1C is equipped with an AIS, automatic identification of ships, antenna, and ships are detected for position, direction, and speed, but the data is available to authorized entities only. At the moment, I can report for you that we need an overhead of 7% in terms of processing to get those products produced, and it's about 1% of the total number of data products in our system. A further slide on the Sentinel-1C data budget. So far, the mission is operational since about spring this year. So we need, you see 7 nodes for level 0, 20 nodes for level 1, 10 nodes for level 2, and then six more. So it's about 36 compute nodes in the production mode with 680 CPU cores and a total RAM of 400 gigabyte. That's that's a nice set of infrastructure. I think in the next talk we hear about HPC computing. That's kind of a low number, I guess, of compute nodes. But I think this is sufficient for the Sentinel-1 mission. In terms of the products, we need for the production about 24% for the level 0 production, 48% of the products of the computation is dealt with level 1 production, and 16% for the level 2 production. The time currency products and the ship identification is then only a smaller part. And we disseminate each day for the Sentinel-1C unit 7.5 terabyte. So, to sum up, I hope I could present that we successfully implemented the Sentinel-1C production workflows in a public cloud environment. We use a DevSecOps, I need to mention, approach for our experts team. We have a very efficient scaling. This you need to believe me, but maybe you've seen it also in the screenshot for the processing. Mainly due to efficient orchestration and memory management within a formative monitoring setup. Also for KPI management in the whole service area. The origins, as you have seen, come from an Earth Explorer processing framework that has been adjusted for Copernicus interfaces and formats. And so we also know that the Earth Explorer generic processing that will come for the future missions builds then on a fully operational backend that is in use for Sentinel-1. Another point, I think this is important, is that with the system that's active for science missions and for the operational missions, we have a parallel evolution of the Sentinel processing services with other Earth observation missions. And this in terms of data formats, the new formats ZAR and COG, and maybe virtual ZAR coming up. In terms of metadata, that we need to provide stack items, stack catalogs, maybe stack labels. We could provide a processor testbed service as for the science missions, and potentially there are upcoming Python algorithms that need to be orchestrated as part of our system. With this, I will conclude. I leave my summary here, and I'm happy to take questions.
Thank you very much, Richard. Very interesting presentation. Audience, do you have questions? Yes, I think we have.
Hello. Just one question. Thank you for the talk. And I'm wondering, you are running on a public cloud, and you use virtual machines on the cloud, not Kubernetes, right?
Our cloud setup is based on a Kubernetes infrastructure management. So
with automatic scale up and down.
With automatic scale up and down. I mean, for systematic production, there is a relevant question if you really need this. Indeed, sometimes the acquisition is not as planned, and then of course you need to be able to scale up and to process in the required times. Yes.
Thank you.
Thank you. And do we have any more questions? Okay, then I have one question. So I'm sitting in the shoes of Asa Beek, and that's why I would like to ask you such questions. So beyond the impressive technical achievements, do you see that that would bring benefits to the broader industry and the space ecosystem? And do you think it can create new startups? And if yes, are you eager to help those startups in their journey?
Well, yes. Thanks for the question. I see what I can tell you there. We've seen. I think this is the important aspect of this whole story. That if you are active in a science environment or active with a new idea in a startup, and you play around with explorative missions like the science missions, then you are ready to use this technology in operational setups, and probably we also need to think always how this can be operationalized. We also heard this morning to commercialize ideas. So I think this is important. We provide our software open source. That's an open approach, but also helps others to join and to join forces and to collaborate on new products and new projects. We hope that we get feedback for this, and that there will be many more ideas.
Thank you very much.
So our next speaker is Johan from the German Aerospace Center. Johan, thanks for coming, and the stage is yours.
Yes, thank you for the introduction, and welcome to my presentation about operational processing of DLR Sentinel-1 normalized radar backscatter product. So we stay in the radar domain, and we take the Sentinel-1 data that is produced by the Copernicus processing service, as shown in the last presentation, and we will go one step further to produce analysis-ready data. Why we are doing this? Because if you access SAR Sentinel-1 data, any user needs to process this data further in most cases. So users need to do calibration, noise removal, geocoding, until, for example, they will get a sigma naught backscatter or also radiometric terrain correction to retrieve gamma naught, which can be used then in further analysis. This is also a CEOS ARD a product that we will generate. We are not building this from scratch. We are based on a prototype and a specification that has been set up by the European Space Agency with a normalized radar backscatter product. In the bottom you see a URL to a description of this product specified by ESA. One important specification is that this product shall be aligned with the tiling and the projection of Sentinel-2 data. So here on the right-hand side, you see a data take of Sentinel-1 individual scenes, which are then split into these MGIS tiles, which you know from Sentinel-2. So based from 26 Sentinel-1 scenes, we have about 200 products for the normalized radar backscatter product. As input data, we use Sentinel-1 ground range detected data, which are about 3.5 million scenes at the moment, with a data volume of 4.5 petabyte. So we use this as an input data to produce this normalized radar backscatter product. We're not only doing this on a daily basis for new data, but also now starting with the processing of the historical data, so for the complete archive. And we have different kinds of output data, ancillary layers, stack metadata, and finally, the data volume of this product for the historical data will be about more than 10 petabytes of data. Of course, there is a challenge to process all the data. So what are the processing steps and what kind of different resource requirements they have? Of course, first of all, for each data take, we need to discover which kind of Sentinel scenes are available. But then for each scene, we need to do the ZAR processing as described before. Then we need to convert to the ARD and the tiling scheme, and finally doing the data publication with validating the data, transferring the data to the final storage, and also doing some cleanup. So we have different tasks with different resource requirements. We have CPU and RAM intensive jobs like the ZAR processing and the ARD conversion. We have data read and write intensive jobs for the data validation, transfer, and cleanup, but also low resource tasks for data discovery and the stack metadata registration, and scaling this up because we want to have a product not finished in 1 year, but maybe earlier. So now the question is, how can we scale it up with these different kinds of computing resources required? First of all, we modeled the process with the business processing modeling and notation language. Our orchestration service is based on this, and here on the left side you see the main tasks, which is then split up into subtasks. Of course, first of all, we query the data, and when we're doing then the ZAR processing, for each scene we can parallelize. We are doing the ZAR geocoding and the validation of the product. And when this is finished for a complete data set, we can go to the next step, to the ARD conversion, where we also do the processing, the validation, and the data publication steps. So the individual colors represents the different kinds of resource requirements. The blue ones are the CPU and RAM intensive jobs. The green ones, the low resource task, and the yellow ones, the data read and write intensive task. So how do we split this in our infrastructure? And before coming to this, I'd like to present our infrastructure, which is named Terabyte, an Earth observation, exploitation, and high-performance data analytics platform, which we built up together with the Leibniz Supercomputing Center. We have more than 50 petabytes of data storage available. We have more than 40,000 CPUs available, hundreds of GPUs, and of course also a lot of RAM available. So first of all, regarding the data storage, we have a data storage management nodes, which is directly connected to the data storage with a high performance network. Here also we pull the data from the Copernicus data space ecosystem into our storage, but also connect our long-term archive, where we also have historical data additionally available. Then we have an on-premise cloud available, where we can deploy our web services like the Stack API, the workflow orchestration service, but also can run tasks of this processing workflow like the Stack registration. And the part with the most processing capacities, we have an HPC system where then tasks like the ZAR processing and the ARD conversion take place. So we can split up our workflow, and each individual task can run on the processing environment, which is best for the individual task. So for the data read and write intensive task, we can use the data storage management nodes as an example. So how do we orchestrate this with the workflow that we have? In our cloud environment, we have our orchestration service currently based on Camunda 7, which is compliant to the business process and modeling and notation language, which I showed before. And on each of the computing systems like the cloud, the HPC, and the storage node, we can pull tasks from each of the processing steps, fetch the task, and execute them on the individual resource requirements, and then return the status. Importantly here is that that we have no connection between the orchestration service to the individual processing environment. For example, in HPC and the storage nodes, we cannot connect from the orchestration service, from the cloud to them. We only need, in terms of security, the connection from the worker to the orchestration service. So how do we scale up? We have a Grafana-based monitoring of available and used resources. And first of all, we can launch a fixed number of processing jobs with high priority that will run always. But then if we see there is processing capacities available, like here on the left, 20% is currently used by other users, so we can scale our processing workflow to use the other 80% of the resources that are not used at the moment. But we can also monitor the CPU resources that we use for this workflow. Here in this graph, you see in the bottom up to 30,000 CPU cores that we have used in this processing. So we can also see how much resources we use at the moment. So finally, I would like to finish with the challenges and the next step. So at the moment, we are based on we are using Central 1 GRD data, but we want to replace this with the Central 1 SLC data because of lower processing complexity to some issues in the GRD data. But SLC data is at the moment, we have data volume of 20 petabytes, so we have them only in our long-term archive, so we need to bring them to our online platform first before we do the processing. But then also for the performance of the ZAR geocoding software, we have started with Snap from ESA, which require a few resources to process. We want to be faster, so at the moment we are transitioning to the Gamma software. Here for one Central 1 scene, we need 8 CPUs and around 60 minutes of runtime. So if we sum this up, to get an idea how long would the processing of the complete archive take. For example, we would need, when we process 1 month, we would need most of the computing resources we have available. So for example, if we would only need 1/3 of the CPUs, because other users we have other users as well, then we would need 3 months to process the complete archive and provide the products to our user. Then ESA is currently doing the re-engineering of all the processor. There will also be a processor available for this NRB product. It is not yet available, but we are looking forward to this, maybe also to include this in our processing workflow. Thank you for your attention.
Thank you. Thank you, Jonas. Do we have any question from the audience? Okay, in the meanwhile, I have a question for you.
Right.
First of all, I'm glad to see that you use BPMN. I'm coming from the information system sector. I'm wondering, all the processing pipelines can be that doesn't run smoothly as you plan. And so I see that probably you still need some human in the loop for error handling and stuff like this. So I would like to, if you can give us some hints how you address this problem.
Yes, of course. So first of all, in our model, you might see this when coming back to the slides. We have modeled that if there is a specific error which we cannot detect or solve automatically, then we have in the BPNN model, there's a human user task. So then somebody is informed to look at the log files and so on. So also in the processing workflow, we store the path to the log files, the access. So it's quite handy to see which kind of scenes are failed and why. And then the operator can go to the expert, and then the expert can look into this, and if he solves the issue, then can just use the system to just parse it to rerun again.
Thank you.
Thank you.
Thank you. And I have the honor to invite our next presenter, Hannes Neuschmidt from Neuschmidt Brackman Consult. And he will be speaking about challenges and solution for algorithm optimization. Floor is yours.
Great. Yeah, just to correct, the company is Brackman Consult. I'm unfortunately not a co-owner. But I will talk about a very long title here and talk a trip a little bit further down the analysis pipeline. Now we're looking at the downstream product. And it's not going to be so much about our computing infrastructure, but more about the challenges that are posed by this specific application and how we can manage to do a production on global scale, 20-meter resolution for Sentinel-2 in a cost-efficient way, so that we can use it multiple times, hopefully. So for some context on the project, this is part of the Climate Change Initiative FIRE project led by University of Alcalá, and Brackman Consult is responsible for the production of this global Sentinel-2 burned area product. And to give you an idea of what the actual product is that we distribute, there are two forms of it. One is an aggregated product on global scale, monthly, on 0.05 degree grid. But if you are interested in the full resolution, we have the 20-meter resolution product split into 5 by 5 degree tiles, also monthly. And in these products, you can find the burned area, the day of the fire, and also a classification by a land cover class, which is provided by the World Cover project. This is the grid product, in this case, for November 2023. Like I said, this is aggregated and not the full resolution. I must also say this product is not yet released, so please stay tuned. But this is a preliminary view that I can share already. This would be an example of the full resolution product in the southeast of Italy. You see most of it is green, but if you look in the bottom left of the image, we see some burned areas, and they're color-coded to be yellow or red, depending on the date of the burn. And if we zoom in a little bit, you can see that in this high-resolution product, you can actually see quite a lot of detail. And my colleague from University of Alcalá has provided a very nice visualization showing 3 months of this same area in different colors. So you see in this 20-meter product, you can actually detect agricultural fires more or less on a patch level, which is not possible with the existing burned area products that we have in CCI already, because they have much coarser resolution. But the main topic of my talk today is actually how this processor works and what challenges it poses for large-scale production. So I have to take you on a journey a little bit to get a basic understanding of how this works. The algorithm proceeds in 2 main steps. First, we compare 2 observations of Sentinel-2 to determine a probability of burn. So in this very simplified model I have here, I've seen a brown pixel, it was previously green, probably it burned. And we do this not just for one pair of observations, but every observation is compared with a number of previous observations from the 40 days before this one. So we get multiple probabilities for the same reference date, and then in the later half of this process, we filter it down. So the second step post will look at these probabilities, take the one with the smallest interval and select that one, in this case the 72%. And then in the next step that is also relevant for the optimization I'm going to talk about, this process I just described will be done for each platform individually. So we have computed a probability of burn for Sentinel-2A from Sentinel-2A time series, and then we will look at the Sentinel-2B time series to confirm or not confirm this fire. So if in the 40 days following and previously Sentinel-2B now saw no fire at all, then we will reject this fire as well. Now, this is all well and good. This is how we got the algorithm. We already did some productions for Sub-Saharan Africa in 2016 and 2019. But projecting how much it would cost to do this same algorithm that we had previously to produce the whole world, it was very clear it becomes very expensive. We have around 3 million Sentinel-2 products that we use as inputs after filtering out some of them that are available for a year, and produce around, I don't know, somewhere below 3 petabytes of data. Our production system, you already heard 2 talks on how these systems works. Ours is similar. It's based on Hadoop, though, and it's deployed on CreoDias, which helps us without a huge infrastructure processing so much data, because we can go to the commercial cloud and we do not have to ingest all the data. So our optimization is based on 2 basic ideas. The one is to pre-process the inputs in a way to make it possible to read only the data that is really needed for this instance. We parallelize by Sentinel-2 image, so by granule, and therefore we previously index the active fires to match 1 granule. Every instance of the algorithm has to read only this data. And the same goes for the world cover map, which is in a different projection and resolution. We match it first to the Sentinel-2 to reduce data that needs to be read. But the main part of our optimization is to take this algorithm that I just described and make it a single pass so that each input of Sentinel-2 is read exactly once. And you will see why this is important in a second. So on the left, you can see the original algorithm, right? We would take 2 images, make a comparison, write an intermediate product. So for each of the pairs of Sentinel-2 images, which are a lot more than just Sentinel-2 images, we have a read of 2 products and we write 1 output product. And we do that again for the next pair. You see already one of these 2 is always the same. Yeah? So we read the same product many, many times. And also, moving on to the next time step, what was previously the reference will now be one of the predecessors, so it's read again and again. And then in the end, all these intermediate products are filtered to arrive at the final probability of burn. So instead, here we already have read these 4 products. They're in memory. We keep them. We would read the next product. Now the previous ones become the predecessors. And we can actually throw away all the intermediate information once we produce a new one, because we will always select the shortest interval for our probability of burn. So the previous ones get overwritten. If we don't see anything because of a cloud, we don't overwrite. And this way, we have to read every product only once for this step. And we also even don't need to write these intermediate products because we will need them in the next step anyway. The question is now, how do we keep this small enough so that we can actually fit it all into little enough RAM to run on commodity hardware and to run many of these processors in parallel? Because suddenly we have a problem, right? From the previous step, we have 40 days of time series that we need to keep for every algorithm. But now, when we want to filter also with a future time series, with what comes after from the other satellite, this amount suddenly doubles because we have 80 days now, 40 days before, 40 days after that we need to keep for both satellites. In this step, we always select the probability of burn of the other time series that is closest to the one that we're currently filtering. In this case, there would be the 90-70%. We saw a fire also in the other platform, so we will keep this one. In this other example, we would see no probability of burn before and after, so in this case, it would be filtered out. Now, this is, like I said, it's too RAM heavy, so we would like to use the same approach we used before. Maybe we just keep the aggregated probability from the future and the past time series and forget about the rest. So in this case, these are the two probabilities that we actually care about. The rest could be thrown away. But unfortunately, now when we move on in the time series, 2 more steps. If you look where the 72% moves, it went from the future to now the past, because we are a few steps ahead. Now we unfortunately forgot about this 0% that is now the highest priority. So we can't actually throw everything away except the aggregation. But luckily, the priority already only increases for those products that come in the future. So we can do an aggregation for the past, but not for the future. This way, we have reduced our 80 days of time series that we need to keep to 40 days again. And now we just need to combine this into a single 40-day time series that we can use for both parts. And this is the structure that we use for this. I hope you can read it on the slide, but in the middle you see the 40 days of time series. And on the left, the oldest product that we still are aware of, that is the one that needs to be compared with 40 days forward into the future. So this product basically waits until we have produced all the previous results for 40 days into the future. Once this is done, we can run our filter, throw this product away, and then move on with this cursor on the left. And if we don't have 40 days in the future time series, then we move on the other side, move the other cursor, open a new product, generate all the intermediate results that we need until we have 40 days of time series again, and then we can move on to the next one. So in conclusion, with the production of a global high-resolution burned area product is quite doable on a cloud like this, but it requires a very involved optimization. And it's not just a case of taking scientific code and maybe doing some technical improvements on it, but we have to really go into the algorithm, break it apart, and see how we can store minimal information in RAM while doing the production, and how we can really fit it to the cloud environment that we're running on. So I hope that was interesting. Stay tuned for the release of the product, and I'm interested to hear any questions. I just wanted to show this beautiful picture also my colleague produced as a yearly aggregation of the global products that we made. Thank you very much.
Thank you, Hannes, very much. Audience, do you have a question? Okay. So then, if I can, I would like to, first of all, apologize for making a mistake in your company name, but I think it's a good upgrade.
No worries.
Yeah. So I have such a particular question. It is very impressive research your team has done, but can you maybe mention one example how it can be commercialized and these results of your research, and maybe for other industry it can be also used? Maybe one example.
One thing, thank you for the reminder that I forget to mention, in a way this is commercialized. This is a service on the network of resources that ESA has ordered to do this production. But can you, repeat the question?
Okay, maybe this can be also used for other industry. Maybe a spin-off from this research can be used somewhere else. So where are you thinking about that?
Okay, it's an interesting question, because the research that we did for this, right, is very specific to this specific processor. So on the one side, we produce this data set which will be available to everyone. So on the data side, this can be used, right, for other industries. On the optimization side, of course, if you have a time series algorithm of any kind that works in this kind of sliding window fashion, you can use the same approach. But I'm not sure I have more to say about commercialization than this.
Thank you. Thank you very much.
Yeah.
Okay, thank you. Our next speaker is Daniel from UMETSAT, and he will speak about cloud native data services at UMETSAT. Please, the stage is yours.
Thank you. Good morning, everybody. I'm Daniel. I work at UMetSat, and these slides were developed together with Misha Ashik, who you might have seen in the course of this conference, but also many other colleagues who have built the services that I'm talking about today. So we've heard a bit about data, about onboard processing, about exploitation on the ground, data production, that kind of thing. What I'm talking about today is data access services, because at UMetSat we operate a number of different missions, and users use our data in different ways. And so we think it's important to make that data available to them in ways that are useful for them. But to take a step back, just to give some context, I'd like to explain a bit, for those of you who don't know, about what UMetSat is. So we are an intergovernmental organization, and you'll see a lot of flags here and a big map of Europe and stuff. What that means is that at UMetSat, we are comprised of a number of member states, and all of those flags are shown for a reason. It's because our primary customers are, and historically always have been, national weather services who are focused on kind of weather and safety tasks using our data. So you could say that our purpose is to deliver operational, so 24/7 by 365, space-based data services. We try to be user-driven, so we try to always understand what our users need. And the purpose of our data is to monitor the weather as well as the climate, including for security and defense applications. But really what we're doing is we're trying to provide data that allows our users to safeguard lives and property, as well as monitor the state of the climate. And we're part of a bigger club of different organizations, so I'm sure many of you know about this already. We've got ECMWF producing mid-range forecasts. We've got UMetNet producing producing observational data that is Earth-based, and then our data flows through this European meteorological infrastructure in order to provide value to the end users. So we try to go from observations, which you see here on the left. We're delivering the data in real time so that forecasts can be made, so that we can look into the future and know about threats and hazards early. And that has kind of determined how our data access worked in the past. So if you come with me into the past, step into the time machine, this is what UMetSat used to look like. So our logo on the left, and down at the bottom you see our archive. That would be for historical data, and at the top we had a thing called UMetCast, and on the right you had users. So we understood our users quite well. They were interested in these kind of real-time things or climate, and for real-time stuff you need the data now, or it doesn't matter, and for climate you can get the data a year later. It doesn't matter if it's delayed. And this dichotomy was something that we lived with for a long time, and it served us well. But things changed over time, and what changed really fundamentally outside UMetSat was that users were getting more and more capable. So there was more computing power, which means that more people were able to use our data. Formats and things were getting more standardized, so you didn't have to write your own software to exploit our data. Also, there's a greater urgency in weather and climate, which is associated with climate change. We were operating more missions, and so we had more observable variables, which meant that there was more geophysical stuff in our data that might be useful to different people. And the infrastructure was just getting easier and easier to get our data out to users. So the internet was robust enough to get a lot of data out to a lot of users, whereas in the deep past, this hadn't really been the case. And so this led to demands from users for us to do better, to make our data more easily available, as well as the thought on our side that there are lots of users who would like to use our data, but maybe they don't know about it yet. And so we wanted to adapt to that. And inside UMetSat, we were operating many more missions than we were in the past. And I won't dwell on this here, but you see lots of depictions of satellites, different orbits and stuff. In the past, our mission was fairly simple. This was no longer the case. And so we wanted to improve things. And that was why we adopted a new data access strategy, which actually, I will kind of read this out. So we wanted to offer a unified, user-friendly, cost-effective access to all of the products that we're responsible for producing, with an appropriate level of timeliness so that the products are useful to people. And the intent behind this is that the services would allow users to use the data, to employ the data, to extract information and knowledge at scale, so that we could support them in their task of safeguarding lives, protecting property, and facilitating informed decisions. And so we transitioned away from this dichotomous world of real-time data access via satellite and archival access. You ask us for something on a tape and we give it to you a week from now. And that is what you see depicted here. So we have a portfolio of data access services now. And Andrea also showed this yesterday. So I'll summarize for those of you who didn't see this presentation. We've got the real-time stuff is still available, so that's the very top. Real-time data gets pushed out to users via satellite and also via terrestrial networks. This is a very high volume service. And we also have near real-time historical and climate data going out via an online data access service called the Data Store. Underlying that is a data lake. And we also offer tailoring capabilities and visualization capacity. And the idea behind this is that we would kind of be building a level playing field that would allow different types of users to find the data in the way that makes the most sense for what they want to do with it. And we wanted to do this in a way that's cost effective because nobody's got any money. Thinking about costs, of course there are trade-offs between costs, resilience, availability, and timeliness. So if you were to view this as kind of a pyramid where the most expensive stuff is at the top, well, that is our very, very robust UMACast satellite service that's at the top of the pyramid here. You can get data in real time, off the grid. You don't need any kind of network. You are really independent of a lot of constraints that might cause downtimes or timeliness issues. And moving down there, you've got then services that have a smaller and smaller footprint in terms of costs, but also are slightly less resilient because they don't have as much redundancy, they're not available off the grid. So looking at the bottom here, and I do not mean bottom to say that these services are of lower quality, they're just trying to do a different thing. We've got the new data services, UMATView, the user portal, which does user management, our tailoring service, the data tailor, our long-term archive, and the European weather cloud is also a thing where it's a compute environment where we allow users to come and use our data in a kind of bespoke environment that is guaranteed to fit their requirements. So what I want to say with this pyramid is that we were attempting to achieve something that was both cost effective as well as giving users the choice of where do I need to go to get the data that I need in the way that I need it. And we wanted to do so in a way that didn't break the bank. So this is a quite transformative thing that started way back in 2017, and the services have been operational since 2020. We got there by first starting off with explorative pathfinders, so we were looking at how do we want to allow users to interact with our data, what are their actual needs. Then we built up a number of services based on hypotheses of what users would need, and when we felt like we were going in the direction that was appropriate, we transitioned to pilots. So in the simile of this bicycle, it's still like a small bike, but these pilots were allowing the users to gain experience with our services in a way that was almost operational. So we were supporting them, but we weren't guaranteeing the quality of service that you would normally get from our highest quality stuff. So the long-term archive, which would never lose data, and UMACast, which would never drop in timeliness. And after getting some experience there, we transitioned into full operations where we've got the quality of service that we consider appropriate for all of these. So for the poll data services, the cloud-based ones that I was showing earlier, those are office hour support 9x5, but they still achieve a much higher availability than only office hours, of course. And that's combined with 24/7 on-call support for the for UMACast, which is real-time service. So in getting here, we've tried to build for the cloud first, so we wanted our deployments to be reproducible. We wanted to reduce the effort associated with rolling things out. We were trying to design kind of for APIs first, containerizing stuff so that it's easy to replicate and easy to keep in control of our configuration. And I'd like to walk you through very briefly how these services look. So if you are a user of our services nowadays, then you might first come to the user portal where you would land and start to learn about what are the services that we have on offer. So you could find out about our data, about the different ways of accessing it, and that might bring you, because you're interested in certain data, to UMATView, which would give you visualizations of the data in question. So here I've just got a screenshot of our GeoColor, so this is geostationary imagery overlaid with our lightning imager. And if you think, oh, wow, this is really cool data, maybe I want to use this in some kind of a workflow that I'm developing offline, you might go to the data store where you could then discover and download the actual data products, not just visualizations, but data that you could use. You might, of course, then take your shopping cart that you've made here and tailor that. So this is the data tailor, and it gives you different options based on what type of data you're wanting to work with. And eventually, if you're building a high availability real-time application off of this, after having developed your workflow there, for many users this is enough, but for those users that need high availability and the lowest timeliness, they can also subscribe to the data either via UMakeCast satellite, which uses commercial satellites to beam the data down to users, as well as terrestrial networks like Géant, and even the internet to get data out to users in real time. So when we were building these, I mentioned before using containers and trying to have a reproducible workflow for rolling things out, which was kind of new for us. These were not services that we were developing as one-offs, but we wanted them to evolve continuously. So doing this all over again, I think that one thing that we would do is try to build in such a way that you can be continuously evolving rather than the way that we'd been doing things in the past, which was build for a mission and then leave it there so it's stable forever. These are multi-mission services. We expect them to evolve and be open to the needs of different users, because we honestly can't anticipate all the different things that users will want to do with our data. So in terms of performance, I just want to brag a little bit. So this is our portfolio. You can access our services in the cloud of your choice, also in clouds that we run. You can use graphical interfaces, APIs, or software clients to interact with everything. With UMakeCast, we're sending out 0.5 petabyte per day to 150 countries, and that works very, very well. In UMet View, it's over 2 million visualizations per day that we serve up, and a lot of these are cached and then further served to other downstream users. In the data tailor and data store, we're putting out over 400 terabytes per month. So it's substantial what these services have achieved. And in terms of architecture, one of the things that's been crucial is that we can adapt it very rapidly. So recently, the WMO brought out a new specification for the WMO information system 2.0. Don't read this, look up the slides offline if you're interested, but the cool thing about it is it's got this kind of architecture that looks like this, where you've got global brokers and caches and a pub sub service where you can subscribe to data that you want, rather than the old push-based way that WMO had of moving data around. And this is architecturally quite different than it was before, but because we'd had this more microservice-like approach for building our services, we were able to adapt very rapidly to implement this using the existing services. So what I want to say is that this allows us to get out more data to more users faster than before, and we can adapt in order to serve up our products in different ways. And as our services, number of users, applications, and missions grows, I believe that this suite, this portfolio of data services will serve us well, because it makes us flexible and allows us to evolve continually to keep abreast of the changes. And that's all I've got to say.
Thank you, Daniel. Thank you for your interesting talk. Do we have any question from the audience? In the meanwhile, the audience think about a question. I have one for you. So it seems like the cloud-native services, let's say, philosophy is like addressing all the issues. So it seems like this is the definitive solution. But is it really is, or do you see any drawbacks? Do you see any challenges ahead of us?
Cloud native is cool right now. In 10 years, it'll sound very, very old. So I'm sure that there will be a new paradigm that will come and wash over everything. I mean, thinking about how we develop software, advances in AI are making software development a very different game than it was in the past. And a lot of the ways that you would have of making your architecture flexible or nailing it down in such a way that your APIs are usable for users long term, I think that may change kind of fundamentally with the adoption of AI. I don't know what that will mean. The biggest challenge that we've had is adapting our way of working inside UMetSat, which is an organization that was originally designed around flying satellites that you launch once and then you never touch, to moving into this paradigm of having services that you evolve continuously to fulfill different needs. So there are organizational challenges to running things in this way, and these challenges have been solved by the wider software world many times over in different ways. So I think learning from what's been happening in industry and ingesting those lessons to our organizations is essential to succeeding.
Thank you, Daniel.
And I would like to invite our final speaker of this session. It will be Vita Fortunata from Plantech, located in the beautiful city Bari. And the topic will be bringing advanced AI directly on board of satellites.
Thank you, chairs. First of all, let me start thanking you, all the organizers here for the event, for giving us the opportunity to present what we do in Planetech and with our partners. I'm Vito Fortunato, and in Planetech I am the coordinator of the innovative Earth observation services named Space Edge, for which an activity within the ESA Incubed program is called AIX as first implementation of this overall program. I know that I am the one dividing you from your coffee, so I will try to be as fast as clear as possible. So telling you a story. And this story comes from what Planetech does since 1994. What we do. We actually, as also highlighted from the panelists this morning, we help our customer to have better or more informed decision using geospatial data and not only. So since 1994, we support our customer with delivery of data, maps, analytics, and services tailored for their needs. And since 1994, and also for the reason why we are here today with this event, we are happy of the avalanche of big data that we are having from institutional mission, commercial mission, and so on, and will be better and better. So as Planetech, we are happy that this is happening, because the more data we have, the more customer we can help with their own business with. But in doing so, since 1994, we have recognized that whether the stream of data and the space assets has been facilitated a lot in this regard, a lot of items are hidden behind these. And these can be considered as a sort of barriers for customer needs to be fully adopted for their own business's decision. And some of these are clearly the missing flexibilities in satellites, in satellite operation. That is actually related to limited autonomy for that. We know that there is autonomy on board, but it's mostly related or primarily related for fall detection items, so for safeguarding the satellite asset, which is an important thing. But we think that also with the advance of high-performance computing on board, that is one of the purpose of this program that we are leading, we can go over this. And what does it mean? We can overcome some of these limitations. So enhancing autonomy on board, enhancing decision-making on boards, even because in most of the cases, for certain time or type of data classes, data are or irrelevant or they are poor quality. They have poor quality. And so what does it mean? In all of these, we are also feeding the downlink with no relevant data. So, and this is an issue that we want to come over. And then, obviously, the opportunity to process data on board is also meant to cover another aspects that is now not totally in line with our customer need, which is having information or elements supporting their own decision at the lowest latency possible. And how we want to overcome this, and this is why our partners, the Orbit, Psycho, and even many others, I would say, and ESA also in this is supporting us, is providing in space a user-centered processing facility that is meant to provide a framework by which, also this morning we will say, how we can push the innovation also at research and innovation at university and so on. So not only customer, but also push the innovation in this. Provide a satellite, a laboratory for all of us, all of you, to make experiments directly on board. And this is one pillar. The other pillar is covering the limited autonomy and low latency items that we are now missing under the hood of the big data iceberg that we see today, is provide access of information at the lowest latency possible. And this is also meant to provide interoperability between satellites. And I will let you see how this is possible. And then clearly, what this building block can provide for sure, testing new mission concept, so testing new ideas directly in orbit, and also lower the time to market for certain type of application. So provide this infrastructure to our customer, but also to many type of users, research included. And now we are going to do this, providing what we call the IX box, which is the intelligent element to be put on board our series of satellites, but the one produced together with the orbit, our partner, and now our group family member, and also together with the possibility to have this box mounted also on other platform. And this what can provide networking element towards the possibility to have lowering the latency by which the information can be processed on board and delivered, or to call actions even inter-satellites, which is another important element, flexibility and autonomy. And on top of this fundamental box, hardware and software, we have pushed onboard services for to be used to application and also for experimentation purposes. And on the ground side, we provide an access to this the flight laboratory, which is what we call an app store, in which we are hosting a series of application and building block that can be used as they are, or can be composed for users to do their own application, or even providing a dev kit, which is meant to provide even simulation for those interested in testing before pushing on board also their the capabilities of their code. And this is a way that we can access these our platform, so a completely web-based, low-code, no-code app store that can serve multiple type of users. This is one of them. We provide building blocks. You compose your application, and then this is directly deployed in flight, tested, and downlinked result. And this is valuable for everything, testing, but also providing commercial services for that then can reside into the App Store and made available to all other users that might need them. And this is just an example of what we are saying. What I was saying, a new way to, as the title of the presentation was suggesting, assess Earth observation data, not only from experimental purposes, and so boost the increase of capacities of the users for their own application, but also simplify the way data are accessed, and even with the onboard resources, having these low latency dedicated channel to either upload the application, even downlink the extracted information. And this is, let's say, a way for doing that. These are the computing hardware that at the moment we are available within the program, and this is actually providing us and providing you, let's say, user, customer, or experimenters, the possibility even to run AI models directly on board the satellites. We have these two configurations because, as we are going to see in a minute, we are having multiple launches this year supporting this program. And this is actually the full picture of the capacity that we are deploying on top of this fleet that we are deploying this year, which are an imaging solution that is provided by a wide field of view camera, which is forward-looking and is meant, for example, to provide scouting information, like, for example, cloud observation. In this regard, one of the concepts that we would like to demonstrate is, okay, if there are clouds, why do I need to have an acquisition? And this is one concept. And then obviously we can support even other types of application that might need this wide field of view, wide swath camera possibilities. And we have also another head, because this is a dual head camera system, which is a narrow field of view camera, nadir looking at medium resolution, and both of these cameras are meant, have been designed designed to support the deployment of neural networks on board, how, in one of the multiple ways, covering the same spectral visible near infrared as Sentinel-2, so from band 2, from band 8A. Because one of the things that we believe that this program, and then in the future might be, is to have constant information flows from institutional mission, and there we might have multiple observers like this that need to be used for specific tasks in this case. And then we have, obviously, last but not least, for two of these three missions that we are deploying and we will be deploying, we have dedicated channels for low latency, the actionable information, so the results of the processing made directly on board, either for experimenting, but also for the operational services that we are building upon for our own purposes, let's say for our customers' purposes, and also the possibility to interact with this intelligent payload unit at low latency. So with a sort of a dedicated channel, which is, I will say, I don't want to say overcoming the normal communication infrastructure of the satellite, but this is done securely. Obviously, we take into account all the necessary things to demonstrate this intelligent onboard processing unit. These are the mission that we are deploying within the program. We have had a precursor mission that has been hosted in one of the orbit launches and capacities that was launched and is now finishing the commissioning period. So we are now starting releases first lights of the satellite's capacity, but this is not having the dual LED camera. It has another RGB camera, but with the same processing facilities, because the overall concept shall remain. The same applies, but with one of the two dedicated low latency intersatellite link channels has been launched in June. Now we are going to start operating these and exercise and understand the capacity, and then the full mission that I showed before is provided to be launched. It is now being shipped to the launch site, is to be launched into the Falcon 9 November launch foreseen. And then coming to application, so which was the starting point. We recognize that we are trying to cover all the elements under the iceberg for that, and what happens is we think that we can cover all the application that might have these four pillars. So the latency is the driver. So whenever we need an alert, we think that this type of system are useful. We need rapid tasking because we need flexibility, we need speed in tasking that. And obviously we need continuous monitoring. And obviously all these is covered by inherent blockchain techniques that are under the hood of the processing facility that we have. These are some examples that we are going to test. These are results from the testing that we did, because we also developed a simulator for that. So just to let you know, you can also have these available even right now. This is an example, building blocks. As I was speaking from the beginning, we are developing this ship detection algorithm with or without AI on board. With this tasking capacity, I was following with a great interest the discussion in the first days in having how we can OSINT task a satellite. Now, for the moment, it's not possible, or at least it's not possible with the necessary latency to be able to respond properly. We are going to demonstrate this type of use case too. And last but not least, we think that, and this is a view that we completely share with ESA in particular, we think that this mission is not to be considered as an EO satellite. Is the starting of the definition, as also discussed this morning, of that digital infrastructure that we are deploying in space, aiming to have a cognitive cloud computing in space capacity. So, thank you for the attention. Any question, I'm here and I will be available for the rest of the day.
Thank you. Thank you, Vito, very much. A very interesting presentation. Any questions from audience? Okay, so, don't see. Yeah, first of all, I wish you luck with your next launch in November. I will be.
Yeah, thanks a lot, indeed.
I really like this app store approach. It opens a big possibility for future, for the commercialization and for new services to arise. Yeah, one like very small question, when do you think it will be fully operational and when it will be open for the market?
The full operationalization of that is foreseen for first quarter of next year. So as soon as launch, let's say, permitting launch, if it is confirmed to be in November, under the the first period of commissioning, and we have also already users, early adopters into our own program. So to demonstrate something that we have developed among all the application that I showed together with them. So I believe that half of next year will be start having to be released and open to the public, but I guess that you can have an early access, for example, to our dev kit, to our simulated data, to start playing around and start getting knowledge of the overall infrastructure. Whether if you are a developer, so we release also an SDK if you are a developer, or if you are a more, let's say, advanced programmer, we have that low-code, no-code guy, and then we have also let's say, the simple configuration element in which you can select your own application among the one that we have already delivered. So this is the target. Early access, operational somewhere in the middle of next year for sure.
Thank you very much, and yeah, please inform us a big network for this, because I think a lot of startups and future startups would like to use your platform.
Excellent.
Yeah, and with this we are finalizing this session.